Imagine sitting across from a loan officer or a doctor and receiving life-altering news. Your mortgage application is declined. A severe clinical warning is added to your medical chart. You ask why, and the answer you get is silence. In human interactions, a decision without a reason is unacceptable. It creates an emotional, practical void. You cannot fix a problem, appeal a choice, or plan your next step if you are entirely locked out of the reasoning process. Yet, as we hand more authority to artificial intelligence, this silent treatment is becoming the default. This forces a difficult question. When an algorithm makes a critical choice about your life, what counts as a real, trustworthy explanation? Navigating the modern world requires us to figure out how to peer inside these algorithmic black boxes without destroying the raw computational power that makes them useful in the first place. Explainable AI, or XAI, focuses on the pursuit of understandable rationale. While simple transparency might allow a developer to see raw code and training data, XAI aims to make the underlying logic meaningful to the people impacted by the decision. We have to distinguish between a model that is inherently interpretable, like a basic decision tree where you can trace the logic step by step from the design phase, and a post-hoc explanation, which involves translating the behavior of a highly complex model after it has already made its decision. This animated diagram illustrates a central paradox in computer science. We cannot run critical infrastructure on simple, interpretable models. High-stakes problems require highly complex, nonlinear deep learning networks, and those networks are, by their mathematical nature, opaque to human intuition. Because we rely heavily on these complex black boxes, we are forced to engineer external translation tools to interrogate them and figure out exactly what they are doing. Instead of trying to crack the black box open and decipher millions of tangled artificial neurons, Explainable AI takes a different approach. It builds a metaphorical glass-walled workshop around the box, an environment allowing us to control inputs, observe pathways, and monitor the outputs. Understanding a model inside this workshop requires two distinct viewpoints. We need global explanations, which map out how the entire system behaves on average, and local explanations, which tell us why one specific individual was denied a mortgage on a Tuesday. To capture the global perspective, data scientists rely on a tool called partial dependence plots, or PDPs. These allow researchers to isolate a single variable and test its weight across the entire system. This animated graph shows a partial dependence plot in action. By holding all other variables constant, we can adjust a single input, like a loan applicant's income, and watch how that isolated change forces the approval probability to rise or fall in direct response. Looking at this technical document, these four individual line graphs display the average variance across predictors in a real banking scenario. Data scientists use these visual readouts to document global interaction trends, ensuring the model's overarching logic aligns with banking regulations. Global trends are excellent for overarching audits, but knowing the model values high income on average does not tell a specific applicant why their specific paperwork was rejected today. To answer that, we have to zoom in. To investigate a localized individual rejection, investigators reach for a tool called LIME. That stands for Local Interpretable Model Agnostic Explanations. LIME creates a perturbation engine, taking the denied applicant and generating hundreds of synthetic, slightly altered versions. By feeding these fakes into the algorithm, LIME maps the invisible boundary between approved and denied, building a simple, readable proxy model that translates high-dimensional math. For an even more granular look, investigators use SHAP, a method designed to calculate the exact percentage of blame or credit each individual feature, like age, salary, or open debt, contributed to the final denial. SHAP draws its roots directly from cooperative game theory, based on a theorem proposed in 1952 to distribute a game's value fairly among players. SHAP treats every data feature as a player and fairly distributes the payout of a prediction among the participating variables. Together, LIME and SHAP empower users to look at a single isolated rejection and definitively weight which exact factors triggered the algorithmic trapdoor. Visual and text-based AI models use a different technique called saliency maps. generating heat maps that highlight exactly what pixels or words the model looked at. But there is a strict caveat here. Attention does not equal intent. Knowing a medical AI looked at a specific shadow on an X-ray doesn't explain why it diagnosed a tumor. This brings us to the most intuitive investigative tool, the counterfactual explanation. Instead of framing the investigation around the fact, asking, "Why was I denied?" the counterfactual investigates the foil. What would it take to be approved? Counterfactuals stand out as the most human-centric tool in the workshop, bypassing complex math to provide actionable recourse. They give users clear directives like, pay off 2 credit cards and your status changes. The glass-walled workshop provides a controlled diagnostic environment, but even a mathematically rigorous explanation can diverge from reality. These tools carry a vulnerability known as instability. A tiny adversarial change in the input data can shift the resulting explanation, allowing bad actors to game the system and hide discriminatory variables behind innocent-looking charts. There is also the causality trap. Explainable AI reveals the statistical correlations the machine relied upon, like noting that a specific zip code correlates with higher default rates. But the machine itself lacks the capacity to understand underlying societal bias or true cause and effect. Furthermore, providing overly precise explanations carries significant privacy risks. By revealing the exact mechanics of a decision, an explanation can accidentally leak sensitive training data or give hackers a blueprint to exploit the model's logic. Because of these blind spots, an AI's explanation can be accurate about its internal math, while remaining entirely wrong about the physical world. Because algorithmic explanations are flawed approximations, they must be meticulously tailored to their audience. A software auditor debugging code requires entirely different documentation than a patient seeking clinical clarity. The danger occurs when we fall into automation bias, the psychological trap where humans blindly defer to an algorithm simply because it generates a neat, authoritative-sounding chart to back up its decision. Explainable AI serves as a diagnostic tool for probing machine output. It offers evidence for review rather than a guarantee of fairness or causal truth. XAI's true purpose is to provide the evidence necessary for human oversight. It ensures when the black box speaks, it doesn't get the final word. The humans in the loop retain the power to investigate, review, and contest the machine.
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.